Hi and welcome to Tutorial 9. In this session, we're going to introduce Poisson regression. We'll discuss why and when we use this modeling approach. We'll review events, counts, incidence, and rates. We'll go over how to fit a Poisson regression model and interpret output, and how to check for confounding and compare nested models. So far in the course, we've discussed linear and logistic regression. Logistic regression, Poisson regression, and survival analysis are all related. With logistic regression, we're modeling if the event occurs, yes versus no, so we have a binary outcome. With Poisson, we're modeling the count or rate at which an event occurs. So rather than estimating the probability of an event occurring, like we did with logistic regression, we're going to be estimating the rate at which an event occurs. And with survival analysis, we modeled the time until the event occurs. So Poisson regression seeks to model the number of times an event occurs over a period of time, while survival analysis seeks to model the duration of time until the event occurs. With Poisson, time is fixed, and we look at the number of occurrences during that time. Whereas with survival analysis, the occurrence is fixed at 1, and we want to know how long until it occurs. Like logistic regression, both Poisson and survival analysis are generalized linear models. So what is considered an event? Events may include death, injury, onset of illness, recovery from illness, or transition above or below a clinically meaningful continuous variable. Events may be a positive event, like recovery from an infection or childbirth, or a negative event, like a heart attack or disease diagnosis or reoccurrence. Recall that an incidence rate equals the number of events divided by person time. This can only be calculated in cohort studies or clinical trials where people are followed over time. This is what we model with Poisson. The denominator is usually person time at risk for the event. Also recall that we can compare incidence rates with a rate ratio, which is the incidence rate of the first group divided by the second group. And we can also calculate a rate difference, which is the incidence rate of the first group minus the incidence rate of the second group. Whenever you report these measures, you should also calculate and report the 95% confidence interval. Also, make sure to know the units of measurement for person time. So is this person days, weeks, months, or years? There's a huge difference in interpretations depending on your unit of person time, so it's critical that this is reported correctly. We use Poisson regression instead of linear regression to model counts or rates. Counts and rates incorporate time. These are the expected number of events over a given period of time. So why don't we just use linear regression to model a count or rate? Why do we use Poisson instead? The first reason is the distribution of the data. Counts follow a Poisson distribution rather than a normal distribution like we had with linear regression. Also, rates include follow-up time as the denominator, and Poisson allows us to count for differences in follow-up time for different study participants. So when do you model counts and when do you model rates? You can model the count, so the number of occurrences, when individuals all have the same follow-up time. When participants don't have the same follow-up time, then we need to model the rate, the expected number of occurrences per unit time. So if everyone has the same follow-up time, we can model the count, the expected number of occurrences. Otherwise, we need to compare rates. A rate in Poisson is also known as lambda. Lambda is the rate at which events occur, the expected number of event occurrences per unit time or per unit space, or y divided by t. So with Poisson, we model the rate as a function of the x's. Some examples of rates include the number of panic attacks in a year, number of sexual partners in 3 months, or the number of overdoses in a certain area. We usually don't know the rate, and we have to estimate it. This rate likely depends on a number of factors. For example, the rate of relapse likely depends on age, gender, ethnicity, etc. So we want to use a multivariable model to adjust for these variables. The same general principles for linear and logistic regression apply, including adding variables to our model to adjust for potential confounding. There are multiple ways to look at the same Poisson model. Ultimately, we're interested in modeling the rate, shown in the first equation. But the rate has an exponential shape to it. As x increases, the rate increases exponentially. So we need to model the log rate as a linear function of the x's, which is the second equation. Similar to logistic regression where we modeled the log odds, this allows us to model the log rate using a line. So this is what we want to model. And this is because lines have simple properties that allow us to neatly summarize the relationship between the explanatory variables and the outcome. And like logistic regression, where we exponentiated the coefficients from our output to get the odds ratio, we exponentiate the coefficients in Poisson regression to get the rate ratio. So this second equation is what we're doing in concept. But the third equation is the way that we actually model the rate with statistical software. In this equation, we use what is called an offset. The offset is the denominator of the rate, usually person time. Even though the offset appears on the right side of the equation, it does not have a coefficient. Instead, it is forced to have a value of 1. Mathematically, the second and third equation are the same. Recall that the logged rate is the logged mean number of occurrences divided by time, which is mathematically equivalent to the logged number of occurrences minus logged time. So we can simply move the offset to the right side of the equation to allow us to do this. But ultimately, the way we interpret our output is as though we have modeled the second equation. So the second equation is what we do in concept, and the third equation is what we model with our statistical software. There are a couple of reasons why we model the third equation, with the number of occurrences or the count as y and an offset. The first is that the count follows a Poisson distribution, while the rate does not. The second reason is that if we just modeled the rate, we wouldn't know how much exposure the rate is based on. So we wouldn't know how confident we can be or how much variability there is with our estimate. So if we just modeled the rate, one event per 5 person years would be treated the same as 100 events per 500 person years, even though these differ in terms of confidence and the variability associated with these estimates. So we have to give the software the number of occurrences, so the numerator of the rate, which follows a Poisson distribution, and the exposure time, the denominator of the rate, or the offset. This allows us to get an estimate of confidence associated with the rate. Whenever you use software to fit a Poisson model, you need to specify the offset denominator, in addition to the count, the numerator. So let's turn to an example using fracture intervention data. The study is a randomized controlled trial of alendronate to prevent fractures in women with osteoporosis. Our research questions are, does the treatment prevent fractures? And does the effect of treatment depend on baseline risk? So just by looking at the variables that we have available in the dataset, you can get an idea of what we're likely interested in modeling. Since we're interested in fractures, the variable number of non-spine fractures should be our count outcome. And we can see that there's a variable for number of years in the trial, so this would be our offset. So ultimately, we're interested in the rate of fractures during follow-up, but we need to specify the count and offset for this rate when we model this using statistical software. So why do we need to use Poisson regression to model the rate of fractures? We can see that the distribution of number of fractures follows a Poisson distribution, not a normal distribution. So most individuals have 0 or 1 fractures, and very few have 2 or more. Also, as I mentioned, there are differences in follow-up time for study participants that we need to account for. We can't just model the count, because if someone experiences 1 fracture during 15 years of follow-up, this is very different than another person who experiences 1 fracture within 6 weeks of follow-up. If we just modeled the count, so the absolute number of fractures, we would lose this information because these individuals would be treated as though they were the same. So this is why we need to model the rate of fractures with a model that specifies the number of fractures as the count and person time as the offset. If all individuals in the study were followed for the same duration of time, we could just model the count of fractures. But because everyone has a different follow-up time in this particular study, we need to model the rate of fractures per person time. Using the R code provided, we can calculate the crude fracture rate for each of the treatment groups, yes versus no. Within the treatment group, the rate is 0.037 per person year, or 3.7 per 100 person years. With the controls, the rate is 0.043 per person year, or 4.3 per 100 person years. To get the crude rate ratio, we simply divide the rate for the treatment group by the rate for the control group. So this would be 0.037 divided by 0.043, which equals 0.85. Our interpretation of the crude rate ratio would be that the treatment group had 0.85 times the fracture rate of the control group. If we take the inverse of this, so 1 divided by 0.85, we can say that the control group had 1.17 times the fracture rate of the treatment group. We can also calculate a 95% confidence interval for our crude rate ratio. How would we interpret this? We would say that we can be 95% confident that the treatment group had between 0.75 and 0.97 times the fracture rate of the control group. So let's fit a simple Poisson regression model in R with number of non-spine fractures as the outcome, person time as the offset, and treatment group as the only explanatory variable. We get a beta 1 of negative 0.159. How do we interpret this, and how do we calculate the rate ratio? The beta is the difference in the log rate for the treatment group versus the controls. So this tells us that the log fracture rate is 0.16 lower for those in the treatment group compared to the control group. And the intercept tells us the log fracture rate for the reference group, the control group. How do we calculate the rate ratio? We exponentiate the coefficient to get 0.85. So note that this produces the same rate ratio as when we calculated this by hand using the incidence rates for the two groups. This tells us that the treatment group has 0.85 times the fracture rate of the control group. How can we calculate the expected number of fractures in each group? First, we need to decide what time period we're interested in. Let's say that we're interested in the expected number of fractures in a group of 1,000 people in the treatment group over 10 years. Recall that the first equation with the offset of person time on the right side is equivalent to the second equation with the offset on the left. So we insert 10,000 or 1,000 people times 10 years into our equation in place of t, as well as our intercept and beta values. We exponentiate both sides of the equation to get the rate, and then multiply this value by 10,000. This gives us a rate of 370 fractures in 1,000 people in 10 years. And this is equivalent to a rate of 370 fractures per 10,000 person years. With Poisson regression, we check for confounding in the same ways we did with linear and logistic regression. so we think this through theoretically to make sure it makes sense in terms of the definition of a confounder. We examine bivariable associations between x2 and x1, and x2 and y. We also examine the change in the coefficient of interest when x2 is added to the model. And we can also use the likelihood ratio test or compare the AIC or BIC to confirm that the variable improves the model fit. As I mentioned, we can compare models using the likelihood ratio test and AIC in the same way we did with logistic and linear regression. The likelihood ratio test is used to compare nested models only and has the same null and alternative hypotheses as we did with logistic regression. It tells us if the residual deviance is significantly reduced with the addition of the variable to our model. In other words, if the model that includes a new variable is better in terms of predictive power. As with linear and logistic regression, we can also compare the AIC of the models. The model with the lower AIC is better. So let's return to our example. Our next research question is, does the effect of treatment on fracture rate depend on baseline risk for falls? So what are we really asking here? Notice the key word, depend. So we're asking, does the effect of treatment vary according to baseline risk? In other words, is the effect of treatment modified by baseline risk? Is baseline risk an effect modifier for the effect of treatment on fracture rate? To check for effect modification, we follow the same process that we did with linear and logistic regression. First, we want to know, does it make sense conceptually that the variable could be an effect modifier? Often with intervention studies, we're interested in testing whether there are subgroups that could benefit more or less from treatment. To check for effect modification statistically, we can either conduct stratified analyses, or we can add an interaction term to our model and test this with a likelihood ratio test. So let's try both ways with our example with the fracture data. First, let's fit a model with an interaction term of baseline risk times treatment included. Here's our output with the interaction term included in our model. We first compare the model with and without the interaction term using the likelihood ratio test. This gives us a p-value of 0.145. So we fail to reject the null hypothesis that the residual deviance of the models are the same. This suggests that there is a non-significant interaction. The model predictive power is not significantly improved with the interaction term added to the model. So this suggests that the effect of treatment on fracture rate is not modified by baseline risk. Let's calculate the stratified rate ratios anyway, following the same process that we did with logistic regression. The calculation of the rate ratio for the effect of treatment among those in the high-risk group includes the treatment coefficient plus the treatment times baseline risk interaction coefficient. We exponentiate the total to get a rate ratio of 1.02 for those in the high-risk group. This tells us that among individuals in the high-risk group, those receiving treatment have 1.02 times the fracture rate of those in the control group. The calculation of the rate ratio for the effect of treatment among those in the low-risk group includes the treatment coefficient only. We exponentiate this to get a rate ratio of 0.82. This tells us that among individuals in the low-risk group, those receiving treatment have 0.82 times the fracture rate of those in the control group. We can see that the rate ratios are quite different. So even though the interaction term was not statistically significant, we might still want to report the stratified rate ratios anyway. How can we get the 95% confidence intervals for the rate ratios? As with logistic regression, this is difficult to do in R when we use an interaction term. But we can fit two stratified models, one for each level of baseline risk. This gives us the estimate of the rate ratio and the 95% confidence intervals for the two groups. Again, we can see that the stratified rate ratios are actually quite different. Among those in the low-risk group, treatment is associated with a significant decrease in the fracture rate compared to the control group, because the rate ratio is below 1 and its confidence interval does not include 1. However, among those in the high-risk group, there is no significant difference in the fracture rate for those who receive the treatment compared to the controls. So the conclusions we draw about the effect of treatment for each of these two groups are quite different. So even though the interaction term was not significant and the confidence intervals for the two stratified rate ratios overlap, suggesting non-significant differences in the effect of treatment between the two groups, we still might want to report the stratified rate ratios anyway, because the fracture rate is significantly reduced with treatment among those in the low-risk group, but not among those in the high-risk group. In the next tutorial, we'll review Poisson regression, including how to interpret output and calculate the log rate, expected count, and rate ratios. We'll also go over the assumptions of Poisson regression and discuss common issues with this modeling method, including over-dispersion and zero inflation. And finally, we'll introduce survival analysis.
Thanks for watching our video. Stick around, guys, because we got lots more.